All right, so this video is going to start on page 17, and we're probably just going to push through to the last pages since this is kind of a review of all that's been covered in this packet. So kind of fast forward to what you need to. Don't feel like you need to watch the whole thing. Okay, but this should cover the ending part of this part one of the packet. So number one, it says define work in terms of physics and mathematical representation. Okay, so remember we talked about work equals a work produces a change in energy. Oops. Okay, so work equals change in energy. And basically the actual technical definition of work is force applied over a distance. Okay, so you had your equations, work equals force times distance or displacement, and work also equals change in energy. What are the units for work? That would be joules. 2, if a physics student pushes a box at a constant velocity with a force of 25 newtons over a distance of 10 meters, what amount of work is being done? So remember, work equals force times distance. So force would be 25 newtons times distance, which would be 10 meters. Multiply those out, and you get 250 joules. If a student pushes down on the same box at an angle of 30 degrees above the horizontal with a force of 28.9 newtons and moves the box same 10 meters, what is the work done by the student? So now remember we have an angle. So I'm going to kind of draw this out very poorly. Let me try that again. Okay, so my force is 28.9 newtons. That is your hypotenuse. I know my angle is 30 degrees. Remember, I cannot use that 28.9. I can't use the hypotenuse. What I need to figure out what is the force actually going in the horizontal direction, or f of x. So remember, anytime we have an angle with the work equation is work equals force times cosine of your angle times distance. So that's all you really need to do. So my force is 28.9 times cosine of my angle, which is 30. And my distance is 10 meters. Okay, so multiply that all out, and you get 250 joules. Okay, 4, what is kinetic energy? Okay, so it is energy due to mass and movement. Okay, so you got to have mass and you got to have velocity in order to have kinetic energy. So what is the equation? So Ke equals 1/2 mv squared. Okay, consider the following problem. A box is accelerated by a force over a distance of d from an initial velocity vi to a final velocity vf. Okay, so we're pretty much just going to go through equations here. So A, remember, equals acceleration is force, or F net, divided by mass. Okay, so that's kind of review. KEI, your kinetic energy of initial, is 1/2 mvi squared. KEF is 1/2 mv final squared. And change in kinetic energy is the whole 1/2 mv final squared minus 1/2 mv initial squared. So it is always final minus initial. Okay, as far as this next part goes, I'm going to skip over this because honestly, it's not going to really do much to help you there. Okay, so 8, in terms of physics, define energy. Okay, so energy is a quantity that can be used to perform work on an object. Okay, so that's the actual definition of energy. Okay, so moving on to the next page. So this is page 18. Okay, so what has more kinetic energy, a car at 30 meters per second or a bus at 30 meters per second? Okay, so they both have the same velocity, but that bus is going to have a higher mass. Okay, so bus because due to higher mass. Okay, so if they both have the same velocity, velocity is not really going to separate them. It's the mass that's going to create that more kinetic energy. 2, a bus at 30 meters per second or a bus at 50 meters per second. So both same bus, okay, but whichever one's going to have the most kinetic energy is going to be the one that's going faster. So if your mass is the same, okay, whichever one's going to have the highest velocity will have the higher kinetic energy. So your answer would be bus at 50 meters per second. And that is due to higher velocity. Okay, part 2 of this one, it says the kinetic energy of a car, the mass is 1,000 kilograms. So a car, 1,000 kilogram car is traveling 20 meters per second. What is the kinetic energy? Okay, so I'm going to plug that in my equation. So KE equals 1/2 my mass, which is 1,000, times my velocity squared, so 20, and that is squared. So do all that math, and it comes out to be 200,000 joules. If a braking force of the car is 40,000 newtons, how many meters does it take for the car to stop? Okay, so now I'm dealing with the same car. Okay, so I know my kinetic energy now. Okay, so I want to know how far does it take, and I was given a force. Now this can be a negative force because it is stopping me. So this is when we get to do the whole F times D equals the whole change in kinetic energy. Okay, so the final minus initial. So what we're going to do is we're going to plug in. So force would be negative 40,000. Distance, I don't know. I'm going to leave it as D. Now, since you are stopping, that means your final kinetic energy would be 0. So you can just mark off that whole 1/2 mv final squared as 0. And this would give you a negative, the initial now, so 0 minus 1/2. Your mass, which is 1,000. Your velocity is still, your initial velocity is still 20 meters per second, and that is squared. Okay, so I'm going to set that equal to D, so divide both sides by negative 40,000, and I get a distance of 5 meters. Now, if the same 1,000 kilogram car is now traveling at 40 meters per second, what is the new kinetic energy? Okay, so let's find out. So our new kinetic energy, so KE equals 1/2. My mass is 1,000. My velocity is 40 now. And that's going to come out to be 800,000 joules. So remember we kind of talked about that is if I doubled the velocity, it's actually going to quadruple my energy because that squared is there. Okay, so if you noticed in part number 3, it said our answer was 200,000 joules at 20 meters per second. And now it's 800,000 joules at 40 meters per second. So number 6, it says, what is the stopping distance required to stop the car from 40 meters per second? So we're going to do the same equation here, same brake force, so negative 40,000. Distance, I still don't know. Okay, and then we're just going to go ahead and do the same thing we did in number 4, so negative 1/2. My mass is still 1,000. And my velocity is now 40. So divide both sides by negative 40,000, and I get a distance of 20 meters. So again, since you doubled that velocity, it basically quadruples everything else. Quadruples your energy, quadruples your stopping distance. Okay, so just make sure you think about that. So our kinetic energy when it was going 20 meters per second was 200,000 joules. When it was going 40 meters per second, it quadrupled, so it went up to 800,000 joules. Our stopping distance for 20 meters per second was 5 meters. And our stopping distance for 40 meters per second quadrupled, so that went to 20 meters. So this part right here is kind of more relationship stuff, so not necessarily mathematical. But when speed doubles, kinetic energy is going to quadruple, or I'm just going to make it easier to write, multiply it by 4. It's because that holds squared. When speed doubles, the stopping distance increases by 4 as well. Now, what type of proportion exists between speed and kinetic energy? Okay, so kinetic energy is proportional, that's what that little symbol means, to velocity squared. Okay, so directly related to velocity squared. What type of relationship exists between speed and stopping distance? Okay, so that distance is also going to be proportional to velocity squared. Okay, so if I double velocity, okay, it would quadruple it, multiply it by 4. If I tripled it, it would actually increase my distance or energy by a factor of 9. Okay, so just got to think about that. That's squared there. Moving on to the next part, it says calculate the kinetic energy of the following. An 800 kilogram automobile moving at 15 meters per second. So I'm going to solve for this. So KE equals 1/2 800, my bad. Velocity is 15, and we're going to square that. So it comes out to be 90,000 joules. 2, a 2 kilogram rifle bullet moving at 500 meters per second. That is a very heavy bullet. Okay, so KE equals 1/2. My mass is 2. My velocity is 500 meters per second. That is moving very quickly. So it's going to have kinetic energy of 250,000 joules. C, a 0.50 kilogram ball accelerated from rest by a force of 8 newtons for 3 meters. Okay, so now mass does not matter because the movement is perpendicular to gravity. So a ball accelerated from rest by a force. Okay, so since my ball isn't going down or up, okay, mass isn't really going to do me any good. Okay, so my force, I gave you force, I gave you distance. Okay, so remember, force times distance, which is work, equals kinetic energy. Okay, because remember, work and energy are the same thing. So force is going to be 8.0, distance is 3.0 m, equals KE. So solve that out, and your kinetic energy comes out to be 24 joules. So again, because that ball is not falling or going up or down, gravity's not affecting it, and then also your mass does not matter because mass is going up and down, and the direction of the ball is going side to side. So D, a stone mass on a 0.25 kilogram string, I'm assuming a string, being whirled around in a circle radius of 2.0 m with a period of 0.785 seconds. Okay, so I've got mass is 0.25 kilograms. I have radius is 2.0 m. And period, remember period was that big capital T, that is 0.785 seconds. So kind of labeled things out. So my velocity, so in order to do kinetic energy, I want to find kinetic energy equals 1/2 mv squared. I have mass, but I don't have velocity, so we need to find velocity first. So if we go back to that whole circular motion unit, remember velocity equals 2 pi r over t. So I'm going to plug in. So 2 pi, my radius is 2.0 over t, which is 0.785. So that means my velocity is going to come out to be 16 meters per second. So now I can actually plug it into my kinetic energy. So step 2, so KE equals 1/2 my mass, which is 0.25, times my new velocity, which is 16, and that's squared. And that comes out to be 32 joules. Now, you can have kinetic energy being whirled around in a circle. So remember we talked about, if I were to ask about work being done, anytime work is moving in a circle, there is no work. But there is still energy. There's still energy that is moving it around. But as far as work goes, that would be a 0. Two small toys, one with a mass of 3.2 kilograms and the other with a velocity of 2.4 meters per second, each have the same kinetic energy of 16 joules. Determine the velocity of the first and the mass of the second. So we are just looking for the missing piece. So each one has a kinetic energy of 16. So we're going to do first toy. So kinetic energy would be 16. I'm going to set that equal to 1/2 mv squared. So 1/2. I know my mass of the first toy. That's 3.2 kilograms, but I don't know the velocity, so I'm going to leave that as v squared. So solve for v, get v by itself, and then take the square root of both sides, and you get a velocity of 3.16 meters per second. So there's answer 1 right there. The other toy, okay, we're going to do the same thing, still has the same kinetic energy, so 16 equals 1/2. I don't know my mass now, but I know my velocity is 2.4, and that is squared. So now you just solve for m, so get m by itself, and you should get a mass of 5.6 kilograms. Okay, moving on to page 20. So page 20, it says a baseball with a mass of 250 grams, so I got to fix that. So 250 divided by 1,000 gives you 0.250 kilograms. The speed of 40 meters per second is caught by the catcher, whose glove moves backward 0.25 meters while stopping the ball. Okay, so what was the kinetic energy of the ball? So kinetic energy, so KE equals 1/2 my mass, which is 0.250, times my velocity, which is 40 squared. And that comes out to be 200 joules. Now, how much work did the catcher glove do on the ball? Now, if this thing's coming in with 200 joules, it is going to take 200 joules to be able to stop it, to make it stop moving. Okay, so it would just be a negative 200 joules. Okay, so you got to think about is whatever energy is it's coming in with has to be the same energy to be able to stop it. If you come in too low, that ball is going to keep moving and your hand's not going to be able to stop it. See, what was the average stopping force exerted on the ball? Okay, so that means I'm looking for force. Okay, I was given distance, and that was a 0.25 meters. Okay, and then we also know we can set that equal to our change in kinetic energy. So we get to use this F times D equals 1/2 mv final squared minus 1/2 mv initial squared. Now, good news is, since we are stopping, the whole final turns to 0. Okay, so force I don't know. Distance was 0.25 equals 0 minus 1/2 my mass, which is 0.25. My velocity, my initial velocity was 40 meters per second and squared. So divide both sides by 0.25 and you should get a stopping force of negative 800 newtons. Okay, number 4. A force of 4 newtons applied at an angle of 45 degrees with a horizontal accelerates at a 2 kilogram disc initially at rest for a distance of 0.50 meters on a horizontal table. So we got quite a bit of information there. So force is 4.0 newtons. I have my angle, which is 45 degrees. Okay, I have a 2 kilogram disc, so I've got my mass. Initially at rest, so that means VI is 0. And I have a distance of 0.50 meters. So I've got a lot of stuff going on here, so let's see what we need to use. So find the work done on the disc. So first you need to find the work. So I'm going to go ahead and draw my angle. Okay, so I got 45 degrees. And I have a force of 4 newtons on that hypotenuse. So remember our work equation, work equals force times cosine of your angle times distance. So force is 4.0 times cosine of 45 times my distance, which is 0.50. That comes out to be 1.4 joules. Okay. B, what is the velocity of the disc after it has traveled 0.50 meters? Okay, so I know my kinetic energy now. Okay, remember, work equals kinetic energy. So now what I can do is I can bring this down here. I can set that 1.4 equal to 1/2 mv squared. So 1/2, my mass is 2.0, and my velocity, so v squared. I don't know what that is. So solve for v and then take the square root of both sides. So velocity comes out to be 1.2 meters per second. Okay. Moving on to the next. Oh, kind of going back onto here. So just because we have everything does not necessarily mean we need to use it. Okay, so just write down everything you have and then go with what you got. So in this case, in part B, all I had to do is take the energy down to part B and then just solve for V. Okay, so moving on to the next page. A 3.0 kilogram mass moving 5.0 meters per second is acted upon by a force of 4 newtons opposite to the direction of the motion. If the object is slowed to a speed of 2 meters per second, what is the change in kinetic energy? Okay, so I've got mass, 3.0 kilograms. I've got the initial, which was 5 meters per second. I have V final, because it slowed down to 2.0 meters per second. Okay, and I have a force, a stopping force of negative 4.0 newtons. So change in kinetic energy, so remember change in KE equals the 1/2 mv final squared minus 1/2 mv initial squared. So 1/2 my mass, 3.0. My V final is 2.0 squared minus 1/2 my mass, 3.0. My V initial was 5.0 squared. So that should come out to be a negative 31.5 joules. Now, the distance moved. Okay, so now we actually want to find distance. So remember, this is when we can do the force times distance equals change in kinetic energy. We're going to save ourselves some work. We already found change in kinetic energy, so we get to bring that down here. So my force was negative 4.0. Distance, I don't know. And my kinetic energy is negative 31.5 joules. So solve for D, and you get 7.9 meters. So 6, a 2.0 kilogram stone whirls around on the end of a 0.50 meter string with a frequency of 2.0 revolutions per second. What is the kinetic energy? So let's label out what we got. Mass is 2.0 kilograms. I have a radius of 0.50 m. And I have a frequency of 2.0 revolutions per second. Okay, so I want to find kinetic energy. So kinetic energy equals 1/2 mv squared. Now I've got mass. I don't have velocity. So I've got to find velocity. So V equals 2 pi r over t. Okay, because we're dealing with a circle. Now, if you notice, I don't have t either. But remember, t equals 1 over f. Okay, 1 over frequency. So 1 over 2 equals 0.5 seconds. So now I have t. So I'm going to plug in. So 2 times pi. My radius is 0.50. And now my time is also 0.5. Okay. This comes out to be a velocity of 6.28 meters per second. So now I have my velocity, so now I can find my kinetic energy. So step 2, we're going to do kinetic energy equals 1/2 my mass, which is 2.0, times my velocity, which is now 6.28, and that's squared. That comes out to be 39.4 joules. Okay, B, it says, what is the centripetal force acting on it? Okay, so this kind of goes back a little bit into that circular motion bit. So remember the equation is centripetal force is Fc equals m times AC. Okay, I have mass. I don't have AC though. But remember, if we have our velocity, we can solve for AC because remember, so step 1 is going to be find AC. That was just V squared over R. So I have my velocity. I found that right here. So it's 6.28 squared over my R, which I already knew was 0.50. So AC comes out to be 78.9 meters per second squared. Now I can actually plug that in. So FC, that's what I'm looking for. My mass is still 2.0. And my AC is 78.9. So this comes out to be 158 newtons. As far as C goes, how much work is being done by the centripetal force? So remember, since if we have a circle, it's attached to the center, so there's energy going on, but your force is pointed towards the center and your distance or velocity is pointing adjacent to it, okay, or tangent, sorry. So if those things are perpendicular, meaning they're not in the same direction, that means there is no work being done. Okay, so again, you can have energy, okay, but if we're asking for work being done, if they are not moving if force and distance are not moving in the same direction, there is no work being done. Okay, number 7. A man pulls with a string on a 20-kilogram mass initially at rest on the floor. He exerts a force of 20.0 newtons horizontally, and the mass moves through 8.0 meters. The mass then has a velocity of 3.0 meters per second. So, first of all, it said we're not lifting the mass at all. Okay, so it's staying on the ground. Okay, so the mass is not going to really be a factor there. Okay, so he initially at rest. So we're going to go ahead and write VI equals 0 meters per second. He exerts a force, so force would be 20.0 newtons. Mass moves 8.0 meters, so I have distance. And the mass then has a velocity of 3.0 meters per second, so that means I have a V final of 3.0 meters per second. So what is the final kinetic energy? I just want to know what the final kinetic energy is. Because we know the initial kinetic energy is going to be 0 because V initial is 0 since it started from a rest. So KEF equals 1/2 your mass. Okay, in this case, we had to use our mass since we're looking for kinetic energy. But as far as work goes, we weren't going to do work there because we didn't have the mass. We weren't lifting it. Okay, so my mass is 20.0 kilograms. My velocity is 3.0, and that is squared. So 90 joules would be your answer. So on this one, what I did is I kind of preemptively marked out that 20.0 kilograms because I just basically read the problem first and I realized that we weren't lifting it. So when you're actually doing, remember the work equals force times distance. Okay, we weren't actually lifting it, so therefore mass didn't really matter. But as far as solving for kinetic energy, so KE, that mass would be a factor. Okay, so that was kind of on me as far as marking that off right out of the gate because I was just reading the problem and just going as I read it. So if you're lifting, mass matters. Okay, if you're doing kinetic energy, mass matters. So B, how much energy is being transferred from the man? Okay, so remember, energy equals work. Okay, so the man is performing work on the box, so work equals force times distance. So my force would be 20.0, and my distance would be 8.0 meters. So the man, that means that person is actually exerting 160 joules of work. But if you noticed, my final kinetic energy is 90 joules. So there's a little bit of difference there. So there's a difference in energy. Okay, so how do you explain the difference to these? Okay, so if the man is putting in 160 joules, but for some reason my final kinetic energy is 90, okay, that means we lost energy somewhere. So 160 minus 90 gives me, where the heck did this 70 joules go? Now, I am dragging this box on a floor. Okay, so that floor is resisting my motion. Okay, so that means I lost this due to friction. Okay, so anytime you lose energy somewhere, if it's sliding down a slide and moving on the floor, okay, usually that's where the energy is going to go because even though the man's exerting 160 joules of work, okay, there's going to be a little bit coming from friction on that. So that 70 joules that we lost is actually just from friction. 8, compare the kinetic energies of two objects, A and B, identical in every aspect, okay, except one. Assume the single difference is object A has twice the velocity of object B. So again, we're talking about kinetic energy. So velocity, object A has twice the velocity. So velocity went up by 2. Okay, so that means the kinetic energy of object A is actually going to go up by 4. Okay, because remember, velocity is squared. So if you double velocity, you're actually going to quadruple that kinetic energy. Object A moves north and object B moves south. So when we did this whole kinetic energy equals 1/2 mv squared, direction had nothing to do with that. Okay, you had mass and you had velocity. So north and south, okay, does not matter. Doesn't affect the kinetic energy whichever way you're going. Object A moves in a circle, object B moves in a straight line. Now, if I was asking about work, this would be a little different because remember, work can't be done in a circle. Okay, but I'm just talking about kinetic energy here. So you've got a mass, you've got velocity. Now, whether it's in a circle or a straight line, doesn't matter. Okay, so does not matter. So no effect on the kinetic energy. Object A is a projectile falling vertically downward. B is a projectile moving vertically upward at the same speed. So again, it's kind of like the north and south thing. Kinetic energy had really no up and down to it. Okay, gravity wasn't affecting it there. Now, gravity would affect this, but as far as your equation goes up here, gravity doesn't have a place in that equation. So direction does not matter. Okay, moving on. Now we got our graph. Okay, so our graph, so remember KE, so kinetic energy or work, any of that stuff, equals, so work equals the area under the curve. Okay, so determine the kinetic energy object at 2 meters. Okay, so at 2 meters, okay, now there's two ways you can do this. Okay, you do have a mass up here, and then you basically, all we need to do is just find the area of the curve. So remember, your y is going to be your force, your x is going to be your distance. Okay, work is equal to change in energy. So my base is 2, my height is 3. So remember, this is a triangle. So remember, triangle is 1/2 base times height. So 1/2, my base is 2, my height is 3. So this comes out to be 3 joules. Next one is I want to know all the way to 6 meters. So 6 meters, I'm going to split this up a little bit. Okay, so this one ended up being 3 joules. Now my box, okay, 2 to 6. That means this has a base of 4. My height goes from 0 to 3 still. So 4 times 3 gives me 12 joules. Now I want to know all the way up to 6. So that means I've got to do 3 plus 12. That comes out to be 15 joules. 11. Okay, so 11, I'm going to kind of draw this here. So we got another box or another square. So my base goes from 6 to 11. So that's 5. My height is still 3. So 5 times 3 gives me 15 joules. Now I want to know all the way up to 11. So I got to do 3 plus 12 plus 15 gives me 30 joules. Now 14 meters, now we got to do the whole shebang. Okay, so I go from 11 to 14, so that's a base of 3. I still have a height of 3. So remember, a triangle is 1/2 base times height, so 3 times 3 is 9. Half that would give me 4.5. Now add them all up. Okay, I'm going to save some time. Just take that 30 we just found in part C and add 4.5, and I get 34.5 joules. What is the final velocity at that 14 meters? So now we know kinetic energy is 34.5 joules. Now, I also gave you mass up here, 3.0 kilograms, so I can just plug this into the equation. So KE is 34.5 equals 1/2 my mass, which is 3.0, and V I don't know, so I'm going to leave as V squared. So solve for V, and you get 4.8 meters per second. 10, a person strikes a nail with a 0.75 kilogram hammer. So mass is 0.75 kilograms, moving at 10 meters per second. So velocity is 10 meters per second. Drives the nail 1.5 centimeters further. So that's your distance, but I can't have 1.5 centimeters, so I'm going to divide by 100. So 0.015 meters. Okay, into the wood. What is the kinetic energy of the hammer? So KE equals 1/2 my mass, which is 0.75. My velocity is 10, and that is squared. Equal it out, you get 37.5 joules. Now, what is the average force opposing the motion of the nail? Okay, so remember, so we're looking for force. So remember, force times distance equals work, which also equals kinetic energy. So force I don't know, so I'm going to leave it as F. My distance is 0.015. Okay, now my final, since I'm stopping the nail, would be 0. So that whole 1/2 mv final squared would be 0 since the nail is stopping. Minus your initial, which we just found was 37.5. So solve for F, divide both sides by 0.015, and I get a stopping force of negative 2,500 newtons. Okay, moving on, last page for this video. How does the kinetic energy of a car change when its speed is doubled? So remember we talked about this. So if we have KE, KE equals 1/2 mv squared. Anytime you change that velocity right here, you got to think about this squared right here. So if I double velocity, okay, my kinetic energy is actually going to increase by 4. 2 bodies of unequal mass each have the same kinetic energy, so both have the same kinetic energy, and are moving in the same direction. If the same stopping force is applied to each, how will the stopping distances on the bodies compare? So it said unequal masses, but they have the same kinetic energy. If you have the same energy, so if both have the same energy, okay, stopping distances would be the same. So one, even though they have different masses, they both have the same energy, so one doesn't have an advantage of the other. The more energy you have, the more energy it takes to stop. So therefore, it would take a bigger stopping distance if you had more energy. 13, how is it possible to exert a force and yet not cause a change in kinetic energy? Okay, so basically what we're looking for is no work is being done. One, the object didn't move. That'd be like me pushing on a wall. I'm exerting a force and I'm expending energy, but as far as work being done and as far as change of kinetic energy, the wall's not moving at all. Okay, so I'm not technically doing any work. 2 is motion was perpendicular to the force. So that means wherever the force was going, my distance and velocity was going perpendicular to that. So that means they were not in the same direction. So therefore, no change in kinetic energy. 14, a bullet with a mass of 12 grams. So mass, I can't do grams. So remember 12 divided by 1,000 gives me 0.012 kilograms. Okay, strikes a stationary fixed block of wood at a speed of 400 meters per second. So my VI is going to be 400 meters per second. Penetrating to a depth of 3.0 centimeters. So there's your distance. But I can't do centimeters. So 3.0 divided by 100 gives me 0.03 meters. Okay, calculate the average net force acting on the bullet. So force is your question mark. And then, let's see, calculate the average force exerted on the wood by the bullet. So that means it stopped in the wood. So that means my V final would be 0 meters per second. So we've got a lot of stuff going on here. I've got force, I've got distance, I've got mass, I've got velocity. So this is where we get to use that fun one. So F times D equals 1/2 mv final squared minus 1/2 mv initial squared. So good news is my V final is 0. So that whole first part of that equation right there goes to 0. So force, I don't know. Okay, so that's what I'm looking for. My distance is 0.03 meters. Equals 0 minus 1/2 my mass, which was 0.012. And my initial velocity is 400, and that is going to be squared. So solve for F, and you get a stopping force of negative 32,000 newtons. Okay, so that finishes up the packet one, part one, and in the next video we'll go over part two.